simulation model is a representation of a real system, and it allows us to make predictions to see what would happen in the future under different scenarios. They're useful because it allows you to do experiments that could be expensive or just impossible to do on the real system. These are often used in climate science or in fisheries. Because the model's a simplification of reality, it inherently means we're going to have some uncertainty. It's therefore important when making predictions to robustly measure and quantify this uncertainty. There are four main types of uncertainty: stochastic uncertainty, parameter uncertainty, data uncertainty, and model uncertainty. To demonstrate stochastic and parameter uncertainty, let's assume that I'm going to give my mate, for his 28th birthday, 28 green Skittles. How many packets of Skittles do I need to buy in order to get 28 greens? I bought 2 packets, which gave me 100 Skittles, 17 of which were green. Does that mean that the proportion of green Skittles is 0.17? No, because if I'd repeated the experiment, I might get a different value. This is due to randomness, and is an example of stochastic uncertainty. Because of this randomness, we are uncertain about the true proportion of green Skittles, which can take any value from 0 to 1. If we calculate across this range the probability of getting our observation, we can then make probabilistic statements about the true proportion. We can use this to predict how many green Skittles we'll get if we were to take a sample of 100 Skittles. If we look across all probable values of the proportion, then we will get a particular distribution. Whereas if we fix the proportion to be 0.17, then we will get a different distribution. Notice that the first has a greater uncertainty. This is caused by uncertainty in the true proportion, otherwise known as parameter uncertainty. Taking account of the parameter uncertainty, to be 80% sure of getting 28 green Skittles, we would need to buy 4 packets. Whereas if we hadn't, we would only buy 3 packets, as we would be overly confident. Now suppose we want to estimate the gravitational coefficient of Earth. If we measure the time it takes for a tennis ball to drop from a fixed height, we can calculate g. I know that the stopwatch has an error that is normally distributed with a mean 0 and variance 0.25. This is an example of data uncertainty. By repeating the experiment, we become more certain about the value of g, but this is still wrong. The true value is 9.81. Our model is an oversimplification that doesn't take into account wind resistance. This is an example of model uncertainty. These uncertainties can have a massive impact on any simulation model. Therefore, it's really important to be able to quantify them, otherwise you end up like me, having to go back to the shop to get another packet of Skittles.